So if you could welcome Gavin Morley, please.
Thank you. Thanks very much, Ali, for the introduction. So, thanks everyone for coming. It's very exciting to be here and to tell you a bit about some of my work and the enormous amount of work that's going on around the world on this topic at the moment. The impossible thing that I'd like to be able to do is to run a computation, to run various different computations in fact, but these types of computations, they would take longer than the lifetime of the universe with the computers that we have at the moment. So certainly not possible at the moment. The way that I'd like to try and do that, to run an impossible computation, is to build a quantum computer, and I'll be telling you, what that means and what a quantum computer is in this talk. And I'll get on a bit later to telling you about Schrödinger's cat here. I'll introduce her as well a bit later. Schrödinger's cat is a way of helping to think about the weirdness of atoms and the incredible ways that atoms behave, the strange things that they do, because these quantum behaviours of the atoms that are so counterintuitive are central to how these quantum computers work. So that's the kind of stuff that we're going to be talking about today. First, maybe let's just think about this word quantum. So has anybody heard of this word quantum? Who knows the word? Yeah. So quantum, not a lot of hands there, but so you're in the right place. So, quantum is the science of the small. This is all about very small things. Quantum theory tells you about how atoms behave, and so that's what we're going to be talking about here tonight. When I say small, I'm not thinking of a small slice of Christmas cake or a small glass of water, okay? So here's a big glass of water, here's another glass of water that's a bit smaller. Here is a very small glass of water. But that is not what I mean by small. So small, I'm talking about, so here's a model of a water molecule. This is the smallest possible piece of water. It just doesn't make sense to try to talk about a smaller amount of water than this. And it isn't obvious that there should be a smallest amount of water or a smallest amount of other things, but this is certainly what physics has found, has discovered, and so this is the kind of thing I'm going to be talking about today. So we've got it's H2O, so we've got that red oxygen atom and the two white hydrogen atoms. So there's one model. Here's another model of the water molecule, but so Lego, I mean, you can build incredible things, incredible structures out of Lego, and in the same way you might say, well, we can look around and our world is built out of atoms in a similar way. But at the same time, particularly, so these models are useful for visualizing atoms, and as physicists we love being able to visualize what the theories that we come up with and try and understand them and try and be able to explain them. But particularly for the purpose of this talk, so these kind of models are a bit misleading, a bit limited, and so particularly visualizing atoms like this as things that we can hold with our hands actually confuses me sometimes, because atoms behave totally differently to Lego blocks, and so it's useful in some cases, but particularly for this evening, you're going to see later, I'm going to tell you later how atoms are utterly, really very completely different from Lego blocks, and so we'll come on to that in a minute. So we'll get rid of these models for now. So quantum physics, like I said, it has these counterintuitive things. I mean, I say counterintuitive. None of us actually grew up in the playground playing with atoms, and so we have our intuition. We've developed our intuition as we've grown up, and that it turns out that doesn't apply to atoms. It doesn't apply to the smallest things around us, and why should it? Maybe there's no reason why atoms should behave the same way as footballs. And so indeed, atoms seem counterintuitive to us, but you might argue, well, why should they seem intuitive to us when they're so alien to what we've grown up with? Who came here tonight? Who used GPS or sat-nav to help find the lecture? A few hands up. So those technologies, those incredible modern technologies, rely very much on quantum physics. So this is not a quantum computer. This is certainly a computer. You know, our smartphones are amazing, wonderful computers. They're definitely not quantum computers, but they make use of quantum physics. So, if, for example, if you want to know the time very precisely, then you use quantum physics, and that's an atomic clock. You may have heard of atomic clocks. Atomic clocks. If you ran an atomic clock for 3 billion years, it would lose 1 second, and that absolutely incredible level of precision is actually something that we find in quantum theory. It's an incredibly precise theory for predicting the results of experiments. Where if it says that something specific is going to happen, then it's really correct. It's really accurate. And so we can use that to build technologies like atomic clocks. And atomic clocks are what end up defining the clocks that we use all around us. And so what's that got to do with GPS? Well, GPS is something that we can use to work out where we are in the world, on the planet, to within about a meter. And that's, again, absolutely incredible level of precision, because you're talking about light that travels from satellites to your mobile phone, and that light is travelling incredibly fast, and so to work out exactly where you are, then you need to know the time again incredibly precisely. And so sat-nav GPS relies on atomic clocks on board these satellites. And so if you want to know where you are or what the time is, then you rely, if you want to be really precise about it, you rely on quantum physics. And so, although I'm going to tell you that there are some very strange aspects of it, at the same time, it really agrees with the experiment, and we have to accept that there's a lot of truth, a lot of reality there in quantum theory, thanks to, as long as you find that GPS works for you, which I always do. And so, so there's a little bit about quantum and computers. So like I said, this is not a quantum computer, but it's an amazing computer. How do our computers work? Well, a simple way to think about it, which is, largely correct, is that they store bits, and a bit has to be a 1 or a 0. A bit is a bit of information, and it either is in a 1 state or a 0 state, and that's what is stored as memory inside your computer, and that's what's processed in the computation. And that's really simple. That's kind of simple. So all your songs on your phone or your iPod are stored as these big long lines of 1s and 0s. It's nice and simple, but then you can build up very complicated computations, of course, from that simple structure. And how do you build it up? How do computers actually do that processing? Well, they use something called a transistor as the basic unit of a computer. So the computer is, at its heart, it's got a very large number of transistors. This is a picture of one of the first transistors. This transistor won a Nobel Prize in physics. Since then, they've got much smaller, but they've still got the same basic idea. The basic idea of a transistor is that it can be in the 1 or a 0 state, so it can store this one bit of information. And you can think of that a bit like a coin. So a coin can be in a head or a tail state. We talk about these things being in these different states, and that's a convenient way to think about things. So this coin has these 2 states, just like a transistor has the 1 and the 0 states that it can be in. And so this is these transistors are physical things, objects, which are storing the information in your computer. Okay, but just storing information isn't what we're talking about here. We could have a piece of paper and write a load of 1s and 0s on it, and that would store these bits of information. But of course, the amazing thing about computers is that they can process this information, and so that's what you get from a transistor. A transistor, say if it flips from the 0 state to the 1 state, then that can control another transistor. That can flip the state of another transistor. And so in this way, really large networks of these transistors are built up together to make to make your computer and to do your information processing. And like I said, transistors have got smaller, but the way they've got smaller is really, really impressive, an incredible feat of engineering over all these years of making transistors smaller so that we can fit more songs onto our mobile phones. So here's a graph I drew to help sort of try and show that. So this is demonstrating, in a sketchy way, it's demonstrating Moore's law. Gordon Moore was the co-founder of Intel. In about 1965, somewhere here, he sort of observed that you could fit kind of twice as many transistors onto a silicon chip every couple of years. So they were shrinking, and you could get twice as many on every couple of years. And this is a really powerful, really impressive rate of shrinkage. And so time starts in 1978 on this graph, when I was born. In 1966 there was a famous football match that was won by, well, the captain was Bobby Moore, nothing to do with Gordon, nothing to do with transistors. But so let's look at this scale here. So in about 1966 then there were less than 1,000 transistors on a silicon chip. But it's increasing. The scale is a funny scale. It's increasing by 10 every step. So this is 10,000, 100,000, a million, 10 million, 100 million, and a billion. It's, huge increase in this capability. We get up to where we are today. More than a billion transistors in the silicon chips in the computers that we have now. And so this is what's driven this massive expansion in computing and the internet that we're making use of now. And just to sort of help you visualize what these transistors look like, here's a picture of one. And the hair, the thickness of the hair on our heads is about 1/10 of a millimeter. This transistor is thousands of times smaller than that. It's absolutely, it's really, really tiny. And this is a sort of a modern transistor that you might find in your computer at the moment. And looking at that picture, you may think, oh, looks like a bit of a dodgy picture. It looks a bit grainy. Maybe the camera wasn't very good. So that's not the case. This is an incredibly impressive picture. And what we're looking at here is actually just the graininess of reality. This is atoms. Each of these dots in the picture is an atom, and that's really, helping you get an idea for the smallness of these things. Not only is this a picture showing a load of atoms, actually this is a mass-produced commercial device that we find and we carry around in our pockets, and it's got this layer here that's just 2 or 3 atoms thick. So these transistors have been designed at that atomic scale, and then there's billions of them on one silicon chip. So that's a mind-blowing, impressive piece of engineering, piece of technology that we have there already, commercialized. And can we take that further? Has that been taken further? So here's an example of where it's been taken further. This is a picture again. We're looking at atoms here, as you might start to get used to this idea. So this is a picture from a university research lab in Australia. And this is a silicon transistor where this atom here in the middle, that's controlling the whole behavior of the transistor. And it's working as a transistor. So this is, again, even more amazing. You've got that scaling down of transistors, and it's basically getting to this level of single atoms. You can see, though, you might be thinking, well, this can't continue forever. The way that atoms get smaller, they can't get smaller, can they? Eventually you get down to an atom and you can't keep on making these transistors smaller and smaller. And to think about that, so here's a model of this transistor, but that's just but so to think about atoms, got here a piece of aluminium foil. It's pretty strong. I think I can tear metal. So I'm going to rip this in two. Okay, so I ripped a piece of aluminium in two. Now I've got 2 smaller bits. So I'm going to put one down. Let's try and make it smaller again. I can rip it again. So that's 2 rips, and I've got a smaller piece of aluminium. How many times can I keep on doing that, do you think? Well, in fact, how many times can you keep on doing that? So if you look under your chairs, you'll probably find, hopefully, a piece of aluminium foil. What have we done? We made a lot of mess, that's alright. But, for example, 16 is a lot, that's very, very good ripping, but I can tell you, you really would not have made it to 76. I can tell you, with that size piece of aluminium, you won't make it 76. So, if you'd have done 76 rips, you would have probably been left holding a single atom of aluminium. Obviously, you would have needed very special equipment to get that far, and then, but you know, what would happen next? I mean, can you rip an aluminium atom in 2? I mean, so again, if you had the right equipment, then in principle, sure, you can rip an aluminium atom in 2. But the key point I want to suggest is that you're not left with 2 pieces of aluminium afterwards. So you're left with maybe a carbon atom and a nitrogen atom. So there's some. As we scale things down, nature gives us some limits along these lines from having atoms. And so that's just a way to think about you know, these atoms that we're going to be talking about tonight. And yeah, back to this transistor, back to this amazing transistor. So is this the future of computing? So is this sort of transistor here going to let us have smaller mobile phones that can hold more songs? And the answer is no, actually. It's a bit like, don't know if you know Henry Ford, supposedly he said that he doesn't like market research. He didn't like market research because his customers would have said to him they wanted a faster horse, and you know, he was making cars. And so in the same way, you know, making the kind of transistors that we have is not what this is for, and is not what I'm interested in actually. What this is good for is trying to make a quantum computer, because we've got this atom here in the middle, and like I said, atoms do weird things. And so if you try and use this as a normal transistor, it doesn't actually work. You just have you know, it's not good as a normal transistor in the sense that as there's a single atom in there, it does things differently to what you would want. And so let's get on to thinking about these weird atoms. So here's Niels Bohr. So he said, anyone who is not shocked by quantum theory has not understood it. I think that's a great quote. And I'm not going to explain quantum theory tonight to you. That might be good news or bad news for you, depending on what you were hoping for. I am going to try and shock you. So I'm just going to try and tell you about some of the weird, shocking things that you find in the quantum world. And so, you know, a lot of this, like I said, this quantum stuff is counterintuitive to me. So I've been working full-time on doing quantum experiments, as Ali was saying, for 12 years at least now. And you get used to the strange aspects of quantum theory, quantum physics, but it never really starts to feel, it doesn't start to feel completely you know, intuitive to me. And so certainly, you know, if you end up feeling a bit shocked by the stuff I'm trying to talk about, then certainly don't worry about that. So let's be more specific. What do atoms do? So maybe you've heard of this experiment before. This is the 2-slit experiment. What this experiment consists of is we're going to fire things at these pair of slits, and you know, they can go through the slits. If they hit the beige colour thing, then they just get absorbed and they're out of the game. But the question is, if we fire things at these slits, what gets through and what do you find on the other side? And to think about this, make use of this pair of slits that we've got here, actually. And what we need next, what I need next is a volunteer, please, from the audience. I need somebody to tell you what you're going to do first. So, we need somebody to shoot some marshmallow guns. So you need to be very enthusiastic. So these marshmallow guns, you really need to pump them to get something happening out of them. Why don't you come up and give it a try? So a round of applause. So, the idea is, you've got to find these two slits, and I'll give you some more advice. You've got to really pump it hard many times, keep going, many times. Keep going. That was a partially successful experiment. So, what we were looking for there was a marshmallow to stick to the stick of that. It's like blue pizza all over again. Let's lift this up. The idea is anyway, you can't see it in back because it's white on white. So the idea is the marshmallow, so this behaves exactly as you'd expect. Your intuition, our intuition is good here. So the marshmallows either go through one slit or the other slit. If they go through one slit here, then we have a pattern of them here. There was a pattern there, they all fell off. But, that's what happens sometimes. And then the marshmallows that went through this slit hit the screen here. And so we have this pattern with two groups of marshmallows. It's all simple, right? Does everybody sort of see that as an intuitive thing that we might expect to happen? Okay, so marshmallows turn out to be a bit pesky, but in actual fact, you know, they're doing what we think that they should be doing. But what about atoms? So let's get my other two-slit experiment. Here's another. Imagine that this is a two-slit experiment which does the same thing but with single atoms. And so inside here, imagine we've got here an atom gun that's firing atoms one at a time. They come and meet these two slits, and when they go out the other side, then they hit a screen at the back. And then I've got a little camera in here which is going to watch the screen and see where the atoms hit. And I'm going to display that up on the screen, and we're going to see a pattern of where the atoms are going through the slits. And so let's run this experiment. Firing the atoms through one at a time and look and see what happens. There's one atom hitting, and then there's a bunch more atoms coming through. And so this looks kind of confusing to me, and that's because most of these atoms have shown up right in the middle. And instead of going through this slit or going through this slit and sticking to the wall on the other side, hitting the screen at the back on the other side, most of them have showed up here in the middle. That's kind of right where they're not supposed to get to. So that's one of these counterintuitive things about what atoms do. What's going on here? So this is a wave effect. This is what this looks like to a physicist is a wave. And I'll show you what I mean with a video. So I got this from YouTube, from this guy Veritasium. He's dunking these two balls into a pond, to a lake, and here's this interference pattern. So he's got one ball here and another one here, and right in the middle is where there's the biggest waves. And then here you can see, on these places like this, then there's almost no waves. And so again, this is kind of something that, you know, we might have seen when we throw pebbles into a lake, but that's, you know, a wave effect that we're familiar with water, for example, water waves, but we're seeing something similar here with atoms, and so that's pretty confusing. And so just to show you that again, you know, this is what I mean. We've got the biggest waves here right in the middle, where there's no gap for the waves to go through. And then, okay, so this was our pattern, remember, from the atoms. So what we're saying, what quantum theory is telling us about this, is that the atom comes up towards the two slits, and it behaves like a wave. It tries out going through both slits at once, and then on the other side, the waves interfere with themselves. The wave of this one atom interferes with itself on the other side, and finally it hits the screen and makes one dot. So that's kind of a confusing thing to happen, I would say, but that's, you know, experiments are pretty clear about this. This is what quantum physics discovers about what atoms do. We have to accept that. That's what the experiments give us. But what about a different experiment? What about, you know, you might be thinking, which slit does the atom really go through? I mean, so, you know, for example, this atom, quantum theory is very clear. The atom does not split into two and, you know, half goes through one slit, half goes through the other. Quantum theory is very clear that the atom doesn't go through one slit first and then the other one. We really have to accept from the theory, which agrees with really well with our experiments, that it behaves like a wave. It tries out going through both paths at the same time. We call this a quantum superposition. We say that the wave, this single atom, is in a superposition of going through one slit and the other at the same time. And so, what else can we do with this experiment? You know, you might be thinking, which slit does it really go through? And so, let's imagine adding in an extra special detector that looks just at the slits and just looks to try and see which slit did the atom go through. Yeah? So that would be helpful, right? So let's try that again. Let's try that experiment again, and we're going to watch it again on the screen. We've got the pattern from the strange wave behaviour there in grey, and here comes another atom. But now we're watching with its special detector to see which slit it went through. We know which slit it went through. It doesn't have to be a person watching, it's just some detector that's watching. So there's one atom in black, and here come the rest of them. Let's see what happens. So it's a totally different pattern, right? It's gone back to what the marshmallows were supposed to do. It's gone back to the sort of normal thing that you expect to find. So some of the atoms have just gone through one slit, and some of the atoms have gone through the other slit. Simple. Except that, of course, you know, that just makes it weirder in some ways. Just by having this special extra detector, we've changed things and put things back to what our intuition might suggest. So that's another one of these weird features of quantum superposition that we have to accept from experiments. Okay, so we have to accept that, quantum superposition. What happens though, you know, so we've been talking about atoms, right? What happens, how about if we have something bigger? How about, you know, a much larger thing, like a cat? What about a cat? So, can a cat be in the quantum superposition? Can we see the same weird effects with something like a cat? Cats can be pretty mischievous, right? They can seems like they can break laws some of the time. Certainly. What about this law of physics? So that's a difficult thing to try and test. A difficult thing to think about. There's no point firing a cat at two slits, right? We wouldn't do that. We would have noticed if a cat can go through two cat flaps at once. We would have noticed. So that's, you know, we have to be cleverer than that. And so there was a very clever thought experiment, an idea for an interesting experiment. It was cooked up by this guy called Erwin Schrödinger here. So Schrödinger thought to himself, can we find some way to look for these weird quantum effects with a cat? And so, to think about that, what he said was, let's do a crazy thought experiment. Let's just imagine we're doing a thought experiment. No one would ever actually try this, of course. It's completely, would be completely unethical. But let's just consider it as a thought experiment. What he was thinking was, let's imagine that we put a quantum two-slit experiment where we would work with a single atom, put that into a box. And as well, we're going to need in there a bottle of poison. And there's going to be, inside the same box, you might have guessed, there's going to be a cat in there, right? It's a thought experiment, okay, don't worry, it's just imagination. So, yeah, what we didn't tell the cat was that there's a contraption in there. So the scientist has got inside there a contraption, right? With the two-slit experiment, this quantum two-slit experiment with a single atom coming along towards a pair of very small slits, so these slits are the same kind of size as an atom themselves. And if the atom goes through the left slit, then this contraption is going to break the poison and kill the cat. Oh. If the atom goes through the right slit, then the contraption doesn't break the poison. The cat survives. Yeah. Okay. So if these weren't atoms, if this was all simple, then we can imagine what would happen, right? There'd be a 50-50 chance of the cat being alive or dead. But these are atoms. Yeah. So like, oops. Yeah. So I was telling you, atoms try out going through both slits at the same time, and so, it's confusing. What's going to happen? Can a cat be alive and dead at the same time? So no, the cat is alive. A cat cannot be alive and dead at the same time. A cat is either alive or dead, as we're used to from our everyday lives. And if you want to understand that a bit more, think about what I was saying about the special detector that goes in there to see which slit the atom went through, right? So for this dangerous, poisonous contraption to work, there must be something which actually looks at which slit the atom went through, and then, if that's the case, we go back to the picture to these black dots. We go back to the simple case of the atom either going through one slit or the other, and not being in this quantum superposition. And so that's kind of how we get back to the world that we know. That's how come we don't experience these weird quantum effects all around us. So, that's the sort of a way of explaining it. At the same time, this is a topic of active research. This is something that I'm doing experiments on actually at the moment. How small is small? So atoms do these strange things. What about somewhat larger things? At what stage does an atom get big enough, at what stage do you have enough atoms together that you lose these quantum effects? And so here in Warwick, we're doing experiments to try and probe this confusing aspect of quantum theory, this boundary between the small and the not so small. And so it's a fascinating, active field of research for us. And so what's all this got to do with computing? What's this got to do with quantum computing? And what I'd like to tell you next is how this quantum superposition, this ability to try out doing two things at once, I'd like to tell you how that's useful for computing, how in fact it allows you to in theory, it allows you to run these impossible programs that I'd like to be able to run. And to think about that, let's look at this coin again. So like I said, a coin can be either, if you toss a coin, it can either be a head or a tail. So here's a coin, here's a head, you toss it, okay, it's a tail. So that's, two possible states. We're going to write them as 1 and 0. So just like the bits can be a 1 or a 0 state. So that's one coin. It's not a lot of money so far there. Two possible states. So here's a little bit more money. We've got twice as many coins. How many possible ways can we toss two coins if we try that? Let's try that. More difficult. Oh, we've got a head and another head. So again, we can have. So it turns out there's 4 possible ways that we can toss two coins. We can either have 2 heads or 2 tails, or we can have a head and a tail. But notice that the 1, 0 is different to 0, 1, because this coin here is shiny, so we can see the difference. It's just like if you're playing football, then if the game ends 1, 0, that's different to if it ends 0, 1. That's the difference between winning and losing. Okay, 4 possible ways we can toss these 2 coins. Let's keep going. 3 coins. 8 different ways, and so what we can see here is these red numbers are increasing, they're doubling. Each time we add a coin, then they're doubling. This is kind of the opposite of what we're doing with the aluminium, where we're making the aluminium half as big each time. And this is a bit like with Moore's law, where we said that you can fit twice as many transistors onto a silicon chip every 2 years, and so that kind of doubling is actually a really large increase once you sort of keep doubling a few times. So, what about taking it a bit further? So, here's, went to the bank, did a £5 note, here's 500 pennies. What happens? You're making a lot of messes. You made some messes over there. So how many ways could these coins have landed? I mean, like, £5 of pennies here on the floor. Any ideas? More than, who thinks, we have a vote. Who thinks there are more than 1 million ways that the coins could have landed? More than 1 billion. More than a billion. Okay. So people with their hands up are certainly right. So total number of ways that these coins could have landed, we can write it as, if you've done some maths, then you might write it as 2 to the power of 500. And what that means is that you start with 2 and you double it 499 times. That is a really big number. So we can write it as 10 to the power of 150, roughly. What that means is we've got a 1 with 150 zeros. I had to make the font a bit smaller so it fits. It's a really, really, really huge number. This is much bigger than astronomically big, for example. This is roughly the number of stars in the observable universe. This is roughly the number of atoms in the observable universe. 2 big numbers. If we multiply these 2 numbers together, and then we multiply again by the total number of stars, we're still a billion short of this red number. This red number is very large. So that's maybe a little bit confusing, right? So it seems like just, 500 coins. How did we get such a big number? And think about your computer. So my laptop has about 2,000 billion bits of storage. It can store that much information, right? So 500 bits. If your computer only has 500 bits of memory, that's rubbish. That's really, you're talking about 1965 or whatever. So how come we've got this amazing big number that seems powerful, but is no use actually for computing? And to understand that, think about how slow it would be to move through all these different states. If you want to do a computation with 500 bits, if you want to try out all of these possible states, one after the other, incredibly, incredibly slow is an understatement. I don't know how to say it more than that. And so that's kind of why a computer with 500 bits is not that useful. And this is where sort of the quantum weirdness becomes useful. So this quantum superposition that I was just telling you about with the atom going through trying out going through two slits at once, that's like saying that a bit, if it's a quantum bit, so we talk about qubits or quantum bits, quantum bit can try out being in the 1 and the 0 state at the same time. So that doesn't sound all that powerful, but if someone could build a quantum computer with 500 of these quantum bits, 500 atoms, then that could explore this super huge number of possible states at the same time. And it's that ability to explore all these different possible paths simultaneously, which is, a good way to understand how the power of quantum computing comes about. And you can think of it as like kind of a parallel processing, if you like, in computing, where you can try out new possible routes at the same time and be much more efficient and much more powerful. So that's a huge space of possibilities. At the same time, having that huge space of possibilities is no use. If you don't know where you are and you don't know where you're going, then there's no help to you. So what we need, of course, is programs. We need special quantum programs that are going to guide us through this huge space of possibilities. And there's only a small number of quantum programs that have been cooked up theoretically so far. The one that's sort of the type of quantum programs that are the most exciting to me to do with things like this. So this is a protein. This is a molecule, and so each dot here is an atom. We've got thousands of atoms there in that protein. There's loads of proteins inside of our bodies, and they're doing really useful jobs. They're, keeping us healthy and well, and that's sort of part of the machinery of the human body. But at the same time, if you're very unlucky, maybe the protein isn't in the right shape. So the shape of these proteins is incredibly crucial to how they behave and how they do their jobs. And if the protein's taken the wrong shape for some reason, then you may have some nasty disease like one of these. And so that's a problem that the medical community face at the moment, of course. In medical research, people do, of course, experiments where they try giving different medicines to people and seeing, if they can find a medicine that makes people better, that cures them. But medical trials are really hard, really, they've got a lot of difficulties associated with them. The impossible program that I'd really love to run would be to simulate the shape of this protein, not just the protein, but simulate also a drug, a medicine molecule, look at how the medicine interacts with different protein molecules inside the human body, and then you could hope to try and run medical trials inside of a computer with simulation. That would be incredibly powerful. It's a far-off dream at the moment, but it's a sort of a motivational, inspiring thing that quantum computers could try and help us out with. Why are we thinking of quantum computers here? Well, so this, like I said, is a load of atoms these atoms obey the laws of quantum physics, of course. So we can, and like I said, quantum research quantum theory is very precise. So we can write down the equations that describe these molecules, these big proteins, but unfortunately there's just too many atoms, and you can't simulate these kind of things just because it's just too big, it's too hard. That's kind of the roadblock for doing these kind of things at the moment. But you might imagine that a quantum computer, you might understand that a quantum computer could simulate another quantum thing like this, because the quantum computer is quantum itself. And so this amazing idea was suggested by Richard Feynman, an amazing physicist, and that would be an impossible, incredible program to be able to run. That would be very exciting. There's a couple of other quantum programs that we know of. So like the one on the last slide, these other programs can solve problems which would take longer than the lifetime of the universe with the normal computers that we have. So Love Grover suggested a way of using a quantum computer to search through a very large database that is containing lots of things that are not in any order, not sorted. And then Peter Shaw came up with an algorithm, a program, that's just a quantum program for factorizing large numbers. And factorizing just means that, we say to factorize 15, we say, oh, it's 3 times 5. So we can do that in our heads, or with a bigger number, we can use a computer. But it gets to the stage where if you want to factorize a number that's big enough, then it's going to take longer than the age of the universe again. And so, factorizing large numbers, maybe that sounds a bit like a hobby for geeks, but it's not really the case actually. So we will use this kind of thing. If you go and buy your Christmas presents on the internet, you give away your credit card details, and they get sent off to the company, but of course they get encrypted before they're sent over the internet, because you don't want someone to grab your credit card details. And that whole encryption is based on the fact that it's very, very difficult to factorize large numbers. And so that's a very real-world application. As soon as Peter Shaw came up with this idea, of course, governments became incredibly interested in quantum computing. I'm not trying to take your credit card details, of course, but governments are interested particularly in being able to intercept terrorist messages that they're sending between each other securely. So again, they use the same encryption to try and, to successfully, communicate between each other without anybody being able to know what they're saying. And so these are 2 more examples of things that quantum computers could do, which would really be impossible otherwise. Okay, I'd like to tell you how to build a quantum computer, but I can't. So there isn't a manual. You can't buy quantum computers in IKEA. There's a great deal of very exciting progress on trying to build quantum computers. There's many possible approaches. There's lots of different ways that people are trying to do it, and they, many different ways that could all work, and are making very good progress towards it, and have already demonstrated simple, small-scale quantum computing, but not at a level that's big enough to be useful to, not with enough of these quantum bits to be able to do something better than the normal computers that we have. So at the moment, it's just at a proof of principle stage. And so, in the time I've got left, I'll just quickly tell you a bit about some of the research that I'm doing, and my team here in the university are doing along these lines. We have labs, like I said, here on campus, trying to explore and push back the technologies that do exist for trying to build a quantum computer. So, this is a crystal of silicon. So we talked about silicon already, and this is a material that I like as well for these reasons, for these purposes. So here's a crystal of silicon. Some of the silicon atoms have been taken out and replaced with phosphorus atoms. And these phosphorus atoms are what is storing this quantum information. Storing this quantum information in this future quantum computer. And these phosphorus atoms, they behave like tiny little magnets. They behave like tiny little compass needles. They can point north or south. And that's how we store this information. So north we're going to call 0, south we're going to call 1. And we can put these tiny little compass needles into this quantum superposition, so they can be 1 and 0 at the same time. They can try out being 1 and 0 at the same time. And to do that, to control what state they're in, we use magnetic resonance. So you may have heard of magnetic resonance from hospital settings, from MRI, that's magnetic resonance imaging. Here's a video of a load of MRI images of my brain. This is, you're looking at my brain on screen now. So I wasn't ill, I wasn't unwell, I was just volunteering for some research, some medical research, which was aimed at trying to understand how we experience pain. Yeah, I'd been going out with a girl for about a week when she took these images. She was rubbing chili cream into my leg and jamming it with a pointy stick and seeing how my brain responded using this MRI technique. So we're married now. So that was a good way, I think, for us to get to know each other. Maybe she wanted to see what my brain looked like before she, took me any further. So magnetic resonance is this way of controlling these tiny little compass needles, which we're using to store quantum information. And that's something that is an exciting part of what we do here in our experiments. In the future, a really exciting goal for me would be to combine these magnetic resonance experiments that I do with this kind of structure. So like I said, this is the red background here is a silicon crystal, and here is an atom of phosphorus that's been put in, not just put in anywhere, this phosphorus atom was specifically put into a chosen spot in this crystal. It's an incredible experiment, but combining this kind of thing with my magnetic resonance experiments is something that is very exciting for me going forward. So yeah, we're coming to the end. I've been telling you how I like to run some possible programs. Here's this kind of idea of the idea of running medical trials inside of a computer. It's kind of far off. It's kind of a far off dream at the moment, but it's really exciting. I mean, so people thought that we would never fly. People thought certainly that we never fly to the moon and back. People thought that it would be impossible to do a heart transplant, right? But these things happen. These things happen now. Research is something that can lead to, successes that are beyond our imagination. And so this is the kind of exciting thing that we're talking about with quantum computing. So with that, I'd just like to say thanks very much for your attention. I'm happy to try and take any questions that you've got.